Hi guys. So far we studied much about electric current. The electric current is contributed due to a charge which is moving. So that we have taken as current I equal to the rate of flow of charge. Flow means the charge is moving. So the current affects. Current causes heating effect, and this is current also cause for resistance. So these kind of effects we learned in the previous concepts. So one more effect due to moving charges. So that effect is very important, is moving charge will produce magnetic field. So in this chapter we will learn how the magnetism is occurring and the interaction of electricity and magnetism. So earlier these two concepts are thought they separate electric and magnetism, but because of the experiment which is done by Oersted. So Oersted experiment made a relation between the current and the magnetic field. Let's observe that experiment and try to understand how the experiment gives the evidence of the magnetic field. So according to history, when Oersted was doing an experiment related to current carrying wire, so he kept near a current carrying conducting wire a magnetic compass. So this is a current carrying wire, a current passes through the wire. To the nearby the wire, so he accidentally kept that compass needle. So this compass needle contains the magnetic material. So that magnetic material which only affects, this compass needle will deflect to that magnetic material. So just like how we play with ordinary magnet and just compass. So but here there is no magnetic natural magnet, just a current carrying conducting wire. So when current passes through this wire, so this compass needle will start to deflect. So that's what the observation he made by the Oersted. When we apply a direct current, so the direction of current, so let it be the direction of current. I is the direction of current. So due to the motion of the charges through this conducting wire, in the vicinity of this conducting wire, so in the nearby the places of the conducting wire, so magnetic field is creating. So that magnetic field is cause, or here the evidence we can get the deflection of the compass needle. So let us play to observe. So this is a virtual demonstration is given by Professor Walter Lewin. So here the cell is connected to a switch and the wire is connected under keeping a compass needle. Again it connected back to switch and the circuit gets complete. When he on the switch, try to observe the compass needle deflection. So when the switch is on, the compass needle is tossed to deflect. So here is pausing due to because the compass needle swings back, but still the current is flowing through the wire. Compass needle is showing the particular direction. Now when we switch or when we change the direction of current, suppose if we change the direction of current now in this side opposite direction, now again the compass needle will deflect in the other side. So when we switch in another direction, now the compass needle is deflecting in opposite direction or opposite to the earlier conditions. Now here the deflection of the compass needle in the Oersted experiment. So a compass needle suffers a deflection when it is placed near a wire carrying an electric current. And when the direction of current is reversed, the direction of the needle also reverses. This conclusively proves that a current carrying conductor produces a magnetic field around it. So this is also known as magnetic effect of current. So finally the conclusion I can say at here, a current carrying wire, a current carrying conductor produces magnetic field around it. So this is the evidence of the Oersted experiment. This is evidence of the Oersted experiment. So finally, I can conclude by saying that a current carrying conductor produces magnetic field around it. Let's try to see one more example. So here, a current carrying straight wire is kept. And to find the evidence of the magnetic field, instead of using compass needle at here, so here are used by the iron filings. So these are the iron filings. So iron filings are nothing but they are the very small powder of the iron oxide. Iron is a magnetic material. So if there is a magnetic field nearby this conducting wire, so we can get the evidence. So when current is passes through this wire, so let the current is passing in this wire in this direction. Now if you can see the alignment of the iron filings, the iron filings are aligning in a concentric circles. So how these circular patterns are coming up? So this circular pattern is the evidence right at here, the presence of the magnetic field due to the current carrying wire. So if I is the amount of current at the nearby this point is at a distance of r, there is magnetic field. So we'll represent magnetic field in the B bar. It's having magnitude and direction. And not only at here, if you can take the nearby point, the strength of the magnetic field is decreasing when we go far away. But when we are close to the current carrying conducting wire, the strength of the magnetic field is very strong. So here that relation is given by Biot-savart. So let us understand the principle of Biot-savart to calculate the strength of the magnetic field due to a current carrying wire. To find the strength of the magnetic field nearby current carrying conductor wire, so the very helpful law is known as Biot-savart. Its pronunciation is little different, so we cannot pronounce this as just like in English. So Biot-savart law says about, suppose I am having a current carrying conducting wire. So let me take current carrying conducting wire. So this is current carrying conducting wire. So this is the direction of current. And I would like to find magnetic field at point P, which is at a distance of R from the current carrying wire. So this is the position vector R bar to find the magnetic field at this particular point. So to find that, first we divide the length into small elemental length. Let this is one of the small elemental length in the conducting wire. So it's having the direction in this direction. So that is the elemental length. So consider a current element dl bar. So it's an elemental length, it's a vector of a current carrying conducting wire. So to find the magnetic field at a location at point P, which is at a distance R. So here R, we consider that as R is a position vector. It's a position vector. Its R roof is a direction. It is along in this direction. So here the vector notation is also important. So to find the magnetic field, so according to Biot-savart's law, so the magnetic field dB is directly proportional to the amount of the current which is passing through the conducting wire. And not only that, the magnetic field at a point is directly proportional to the length of the conducting wire. So here I consider small elemental length as dl. And the magnetic field at a location is inversely proportional to the distance from the conducting wire. So if the distance is more, as per it here, if the distance is more, the magnetic field strength is less. So that's the inverse relation it follows. So magnetic field and the position where we find the magnetic field, so that is inversely relation. And one more very important, so the magnetic field, the small magnetic field is directly proportional to sine theta. So here theta is the element. Suppose if I draw a perpendicular at the elemental length through elemental length dl and the position vector r, so this is the theta. So dl, the dB is directly proportional to, so in this figure if you can see, the dB is directly proportional to the angle between the elemental length theta and the position vector r bar. So if we combine everything and write, so dB is directly proportional to I dl sine theta upon r square. So this is the magnitude of the magnetic field at a particular point. So dB is directly proportional to I dl sine theta upon by r square. So we will remove proportionality symbol by placing a proportionality constant. So it's a proportionality constant k. We can consider that k times ideal sine theta upon r square. So here k we call as proportionality constant, which equal to mu naught upon 4 pi. So here mu naught is nothing but the permeability. So we can call that as permeability of the given medium for free space. So finally I can express that dV equal to mu naught upon 4 pi times ideal sine theta upon r square. So this expression gives the amount of the magnetic field at that particular location. So magnetic field is a vector, it's having direction, or that we can get from at this particular formula if I rewrite this above the formula. So by multiplying and dividing with a again position vector r, so multiply and divide with r on both sides, sorry, on numerator and on the denominator. Therefore dB equal to mu naught upon 4 pi times IDL r sine theta upon r cube. So here r is a position vector and dl is also a vector, and if you can write this in terms of vector notation, so the direction dB bar, which equal to mu naught upon 4 pi I times, so here dl cross r bar upon r cube. So here r bar and dl, they both are vectors and the cross product of two vectors, so that becomes dl bar cross r bar, which equal to dl r sine theta. So that is the cross product of two vectors, or if you remember, a bar cross b bar equal to ab sine theta. That is the cross product rule. So it means in the position vector, the component of the r sine theta, so this is contributing a component, r sine theta component is contributing along with this elemental length. Now that cross product, we can get final expression, the magnitude and direction of the magnetic field at a given point, dB bar equal to mu naught upon 4 pi times dl cross r bar upon r cube. So how to recognize the direction? So to recognize the direction at this particular case, means the direction of dB bar. The direction of dB bar. So the direction of dB bar is a vector, so its direction is perpendicular to dl bar cross r bar, and it is given by right hand screw rule. Right hand screw rule. So we have basic knowledge about the right hand screw rule. Suppose place a right hand screw at point P, so where I would like to calculate the magnetic field. So at this location, place a right hand screw, so on the plane of the paper, and turns the handle dl bar on the r bar. It means here the elemental length dl just turn in the theta angle direction. So that is the rotation of dl over the r along the theta. So it means the dl is rotating in clockwise direction. So when you rotate screw in clockwise direction, where it will be move. So the corkscrew rule direction, it advances inwards. So then the direction which the screw advances gives the direction of dB bar. So we can use that conventionally. That is the convention direction. So thus the direction of dB bar is perpendicular into the plane of the paper. So at here we can represent as it is perpendicular. So we will represent that with a cross mark. So this is vector notation cross mark perpendicularly how the screw is advancing. It is advancing inside the screen. So in this we can use two type of conventions. Since magnetic field is a vector is represented two ways. One is a point and one is cross. Point means if it is the arrow. So suppose if I take an arrow, if this arrow is coming out from the page, so the tip of the arrow we see first. So this represents the magnetic field is coming out from the page, and the arrow contains the back as a cross, so like this. And when you draw a cross mark, it means the magnetic field is going inside the page or inside the paper. So the dot and cross are the two conventions here we use it. So the dot represents the magnetic field is coming out of the page, and the cross represents the magnetic field is going inside the page. So here the same convention if you follow, the screw is advancing. The screw is advancing into the page. So that's why we represent the magnetic field direction at here with a cross mark. So finally the magnetic field dB equal to mu naught upon 4 by times ideal sine theta by r cube. Suppose if you take a case, so that case is first one. Suppose to find total magnetic field. So till now we calculating B. Now to find the total magnetic field, earlier we consider an elemental length dl. Everywhere it's considered an elemental length dl. So if this small tiny elemental length contributes an elemental magnetic field. Now to find the total magnetic field, we need to consider the total length of the conductor. So we can do integration. So to find the total magnetic field, total magnetic field B, so we can do the integration dB within the limits, integral closed integral. So within the limits we can do the integration to get the total magnetic field. And since magnetic field is a vector, suppose if theta equal to 0 degree, it means the angle between elemental length and dl and the position vector. So this theta value becomes 0. If theta value becomes 0, so sine 0 will give a result of 0. Therefore the magnetic field in that particular case goes to 0, means which is minimum. The angle between the elemental length and the position vector where we need to find, so that value gets 0. Now this is the minimum position. So this is along the axis. Therefore, the magnetic field is 0 at points on the axis of the current element. So on the axis of current elements, the magnetic field is 0 because the elemental length and position vector, so they are making no angle. So that's the reason. Now if magnetic field is 0, when it will be maximum? If theta equal to 90 degree, it means if it is the dl elemental length and this is the position vector r exactly perpendicular. Suppose if I take an elemental length dl bar, so this is the dl elemental length and this is the position vector which is making an angle of 90 degree. If theta equal to 90 degrees, therefore sin theta value gives 1. So dB equal to maximum, or otherwise the sin value always oscillates minimum 0 and maximum 1. So the magnetic field due to current element is maximum. So the magnetic field due to current element is maximum in a plane passing through the element and perpendicular to its axis. So the maximum magnetic field you can get at a point where the elemental length is perpendicular to the position where we selected. So there we can get the maximum magnetic field. So this is all about Biot-savart's law. And let us try to find the unit of the magnetic field, the SI unit. The SI unit from Biot-savart's law So from this we can get the SI unit of magnetic field is Tesla. This we can call Tesla. Yeah, it is, the name came from the Nikola Tesla. So because he is the pioneer to interrelate electricity and maximum. So dB equal to mu naught by 4 pi by ideal sin theta by r square. Suppose in that particular case dB equal to mu naught upon 4 pi I dl sin theta upon r square. Now in this case, if current I equal to 1 ampere and the elemental length dl equal to 1 meter and the distance position vector is also 1 meter, then theta is maximum 90 degree. Then if you can get that all the values, if you can substitute at here, dB equal to mu naught upon 4 pi times the rest of the values, everything will becomes 1 times 1 times 1 upon 1 square. So if theta equal to 90, the sin theta sin 90 value is equal to 1. So we can get dB equal to the elemental magnetic field mu naught upon 4 pi. So mu naught value for the permeability, it's a 4 pi times 10 power minus 7 upon 4 pi So these two values gets cancelled, which gives a number 10 power minus 7 Tesla. So here we can define directly dB equal to 10 power minus 7 Tesla. So now we define 1 Tesla. 1 Tesla is 10 power 7 times the magnetic field produced by a current carrying wire of length 1 meter, and the wire is carrying 1 ampere current at a distance of 1 meter from it is perpendicular to it. So 1 Tesla is a 10 power 7 times magnetic field. So 10 power 7 times magnetic field produced by a current carrying conducting wire of 1 meter, which is at a location of 1 meter distance, and the angle between the position vector and the magnetic current carrying conducting wire is goes to 90 degrees. So this is something we define as 1 Tesla. So 1 Tesla equal to 10 power 7 times the magnetic field at that particular location of a current carrying conducting wire of length 1 meter, and here current is also 1 ampere. The current through the elemental length is 1 ampere. If 1 meter wire carries 1 ampere current, so at a distance of 1 meter location, the angle made by the position vector and the elemental length of the wire equal to 90 degree, then we define that as 1 Tesla is the magnetic field at that particular location. So this is all about the magnetic field due to current carrying conducting wire. So due to that current carrying conducting wire, the magnetic field is produced around it. So if you try to compare the electric field and magnetic field, so you can notice some similarities and some differences, electric field to magnetic field. So electric field we represent according to Coulomb's law. According to Coulomb's law, the electric field equal to 1 over 4 pi epsilon naught dq upon r square. Magnetic field according to Biot-savart law, so dB magnetic field equal to mu naught upon 4 pi times I dl sin theta upon r square. Now let us find the similarities first. So the similarities are, first of all, the both fields depends inversely on the square of the distance source. So they both are inverse square laws. So D is directly inversely proportional to r square, and dB is also inversely proportional to r square. They both are inverse square laws. And second similarity is that magnetic field and electric field both are long range fields. They both are long range fields, because inverse square law, when the r is increases, the strength of the field is decreases, but they will act in the long range. And the third similarity you can say, so they both follows, it's very important, principle of superposition. So they both follows the principle of superposition. So these are the noticeable similarities. And what are the differences? Let me discuss main two differences. So the first thing is that magnetic field is a vector, but electric field is a vector source. But electric field is produced by a scalar source because of the charge. So here magnetic field is producing due to because of these two factors. dl sine theta is a elemental vector source, and but here the electric field is producing due to because of charge. Charge is a scalar source. So that is one of the difference we can notice. And the direction of the electrostatic field is along the displacement vector joining the source and the field points. Yeah, when you find the electric field direction, it's a vector that is joining the source and corresponding field point. But at here, the direction of the magnetic field is perpendicular to the plane containing the displacement vector. So the first difference is in source. Magnetic field is a vector source. Magnetic field is a vector source and electric field is a scalar source. And the second one, the direction. So the direction of the electrostatic field is along the displacement vector joining the source and the perpendicular electric field, but the magnetic field direction is perpendicular. And one more point, so that is the second one, direction. And let me take the third one. The Biot-savart's law, the magnitude of the magnetic field is proportional to the sign. So in the Biot-savart's law we can find that magnetic field is directly proportional to sine theta. But in the electric field we do not depend on any angle. So electric field is not depend on any angle. Yeah, this is one of the difference we can find. So the electric field is independent of the angle factor, but the magnetic field is dependent on the angle factor. So this is all about the Biot-savart law, so which gives the amount of the magnetic field at a point due to a current carrying conducting wire. So finally I can conclude by saying a current carrying conducting wire is a source of magnetic field. So the direction of magnetic field due to current carrying conducting wire can be calculated by using right hand corkscrew rule, and the magnitude will be found by using Biot-savart law. So dB equal to mu naught upon 4 pi times ideal sine theta by r square.